Hubble Space Telescope. I'm an engineer. I don't claim to be an astronomer, so if you ask me astronomy questions and I answer them, I get extra points. If I don't answer them, then I don't answer them. So I'll try my best to either lie real well, or you think I told you the truth. That's not true. So I'm going to talk a little bit. Now, I broke this one up into little sections so you'd know when I jump from one topic to another, because I want to cover a lot of things and I wanted to make some clean breaks there, so I put some slides in there. But I'll start out with basically, Hubble telescope, hands. Have you heard anything about it? Have you heard that it had some problems when they launched it? So one of my best friends, let me see if I can get this right, my best friend's wife's sister's daughter works in public affairs for Hubble, and she sent me some information to look through and use it during the presentation, so that was helpful. I don't know, don't ask me to do that again. So we're going to cover a few different things. We're going to look at how Hubble works. We're going to look at some of the problems they had with it. We're going to look at we have to have some tools to understand astronomy, so I'm going to talk about something called astronomical unit and light year. Has everybody heard of astronomical unit and light year? Just pick one. So I'm going to try and do some things that are impossible to so I'm going to cover the Hubble Space Telescope, some of the problems that it had and how it works. I'm going to cover some issues with. Well, there's a speaker right here, so it's probably.
I think it's the mic, but he's not back there, so.
Yeah. Keep trying. So we're going to look at. We're going to need some tools for astronomy. We're going to look at some astronomy. We're going to look at some cool pictures, and we're also going to try and understand why it's time travel. So, I mean, a lot of y'all are going to know this, but just act like I'm doing something special. So I went through this thing like 3 times. I'm like, well, the first question out of the box is going to be, who's Hubble? So why is the telescope named Hubble? So we had an astronomer that passed away in 1953. He has some pretty interesting things that he found out. He was an extragalactic astronomer, is that right? Yeah, say that 3 times fast. And he found out that a lot of the scientists of the day were saying, hey, these fuzzy things in there are really just balls of gas in our universe. Well, they turn out to be galaxies or dwarf galaxies, specifically Andromeda, larger Mesomonic cloud, and the lower Mesomonic cloud, which we can see those two if we have a good telescope and a good clean night. We might be able to see those with our binocular. I did see last night the little nebula around Orion's sword, so that was pretty cool. So he came up with this idea through a bunch of research that everything is receding, flying away from the Earth, which basically in a day or so increased the size of the entire universe. So this is his slide that he had that helped him prove that. So he had found 3 things on there that were basically novas blowing up. So after looking at it a little bit, he found out one wasn't actually blowing up, it was varying in amplitude and brightness. So he kind of surmised from another lady's work, let's see if we can find her, she found out that if you knew the period of that cycling, you could determine the brightness of the star. And from the brightness of the star, you can determine how far away it is. So when he looked at like Andromeda, he found out that it was like 2.5 million light years away. So it went from an understanding that things were only thousands of light years away to millions of light years. And this basically happened very quickly. Once he figured out how far, the day he did the calculation, the universe just jumped by 3 zeros in size. And now we know it's billions of light years across. So that's why he gets credit for this, and that is the recession. He was able to measure them and find out through other means that they were moving away from the Earth is Hubble's law. We're going to talk about that a little bit more. But this is some of the charts that he came up in the measurements with. He did. So now we're going to actually get to Hubble. So this is the telescope flying on orbit. Solar panels, the door in front is in case they have to maneuver where it might actually look at the sun by accident, because that would be the end of the telescope. So they have a door on there. If they feel like there's some kind of danger from flying debris or something like that, they can also close it for that. But the back half there is where we're going to go work here in a few minutes. That's where all the instrumentation is. And the mirror is right there behind the back line of the solar cell. If I could use this. So the mirror is right in here. This is where all the equipment is. This is just the focal length of the reflectors inside. So the first question is, why put a telescope in space? Well, everybody liked going to the beach. If we didn't have an atmosphere, we'd all burn up. The radiation out there would be just terrible. We'd get skin cancer and burn. So The atmosphere is actually a good thing. It knocks things down, but it also absorbs a lot of light. The light coming from the sun, the ultraviolet, visible, it's all knocked down. For example, when the sun's setting, it's orange. Why is that? Because it's knocking all the blue visible light out of the spectrum. That's why you can look at it, because you're looking through a lot of atmosphere. So those things are in the way when you're on the Earth. So all the telescopes on the Earth have to deal with that. In fact, the astronauts on the Apollo program were amazed at how blue the Earth was because there's none of that up there. Plus there's also dust and particles. The wind's moving, makes things twinkle, like when you see a star twinkling, that's because of the stuff in the atmosphere. They get by all that. They also take on the burden of being in space, how expensive that is to maintain and repair a telescope in space, which Hubble was designed to be maintained and managed in space. So you get around a lot of that by being on Earth. You get a clearer picture of the light coming into the telescope, so you can get, and if you go to have your picture taken, what do? They flood you with light, so you get all that light back. So this is the transporter for the, we'll take it out to the pad. Okay, you can fact check me on that if you like. This is actually the transporter, so all the payloads, this can actually lay down or stand up. So they put this in there, take it out to the pad, and they can actually put it in the pad, or they can move it in the OPF and take it up there. So we don't use the bus, that's just to give you an idea of how big it is. So it weighs about 24,000 pounds, about 50 feet long. And the $16 billion cost, which is astronomical, comes from the 5 or so missions as well to get it up there. I think James Webb is around 10 billion. Still very, very expensive for what they're doing. And as somebody asked me a little earlier, the end of mission is going to be somewhere between 2030 and 2040. But they got it on orbit, and they found out they had a problem with it. There's somebody here that actually knew the term spherical aberration. Somebody, are they in here? Fess up. So they found out that the mirror was ground wrong, and it gave them very furry images. So the ability to separate two objects is what we're looking at. So the bigger the mirror gives you the ability to distinguish between one object or another. And that's what gives you that depth of field, because then you can go a little deeper, and at some point you can't separate them. They even do things like take pictures on this side in June, and then they go back in December, and the other side of the Earth, they take more pictures so they can get a bigger distance between, to increase that angle. And that's how they started measuring distances to galaxies and things like that. So here's the guys grinding the mirror. This guy I covered up with the null corrector tool. I don't think he minds so much because they ground it wrong. So they had a calibration tool, and the problem was that they calibrated the tool wrong. So the tool they're using is wrong. So they can't get a correct mirror, but the good thing is they got a good mirror. It's just perfectly ground wrong. So there was a lot of strife between NASA and the contractor, and so that led to them being frustrated at cost overruns and not doing a test that they should have done that would have caught this. There was a backup plan, though, and I'll get to that here in a minute. So this is the mirror, and here's what they're going to end up doing. They're going to put glasses on it. So they're going to bounce the light around a little bit so that they can fix the focal length and fix the glasses. And they're going to put 5 sets of glasses on it. So here's them on orbit, playing with it. Get a scale of how big it is. To something in space, because if you push on something, it pushes your way. So they have to actually get on an arm or have foot strengths to open and stuff like that. So even though something is very heavy and it's easily to move, it moves you much easier than it moves. So you have to be bolted to something. We're going to show that in a second. But it was designed with nice doors that you could open, and these are all plug-in like sockets. They just plug in there, plug out. So it was designed to be repaired on orbit because you don't have the dexterity and everything to hold little bolts and things like that, which will lead us to a problem here in a minute. But this is the corrective optics that they put in called CoStar. So it's basically a set of glasses. They took an instrument that was in there, and they pulled it out. So they did lose some capability, but now they had a telescope that would work. It's about 600 pounds, the size of a refrigerator, so it's pretty heavy, but it doesn't weigh per se. It has mass to it, so they have to be on the boom there to move it around and put it in. But one guy can easily pick it up. In fact, in one case, they had a guy that was a The grappling device, the payload that they were trying to catch, did not work. His name was Moose. He worked for a company that built the telescope, and they just stuffed him in a spacesuit that was too small, and he went on orbit, and they said, just reach out and grab it. He just reached out with the arm and grabbed it and held it, and then they moved it over as he held the whole satellite and set it down, and they brought it home. So they didn't leave it on orbit. That was freaky there. So these are the optics that they put in. They're just little mirrors that they go through to get the right focal length. And they also replaced another camera called the wide field planetary camera as well. And this is the difference. So you can see how fuzzy this is, and it's really what you're looking for is the ability to take two stars and be able to see the difference between them. So this looks fuzzy to me too. What they're really going for here is the ability to separate it. That means they can actually pull into the picture more and get a finer picture out of it. So much is how things are. NASA, in their infinite wisdom, decided to build two mirrors. This thing, in case something happened in the first one, but they didn't check the first one. So they had hired out Kodak, company to make a mirror, and they made one. And Kodak offered to go check the other one, and have Lockheed Martin come check theirs, just as check, but didn't do it. This mirror is perfect. So if they had put it on there, they would not have had a problem. And the sad thing is that they never used it for anything. They just kept it there, and nobody ever used it for another telescope or anything. So kind of left behind. So now I'm going to kind of jump just a little bit, and we're going to get into a couple of other repairs. This is Mike Mezzaneo, known as Space Hulk, and you'll see why here in a minute. They had this. He'd flown a couple of missions. They had this bracket, and this bracket went over one of the doors. I don't know why they designed it that way, but it was basically blocking one of the doors from opening. And they took 3 of the screws out, the 4th one would not come out. Tried and they tried and they tried, they could not get it out. So everybody was thinking of all kinds of ways to get this out, and Mike said, well, why don't I just break it off? And everybody's scrambling around. So somebody on the ground got down there, and they got a scale, and it said, it breaks about 60 pounds. So they said, hey, we think you can break it off. And then the next group of NASA people come along, oh, you're going to get debris, it's going to break off, it's going to go into the telescope and mess up the telescope. So no. So they put lots of tape around it. And then the next group got involved, well, he's going to poke a hole in his spacesuit, and we're going to have a problem. So NASA's very paranoid. So after they got by all that, they finally went to go do it, and everybody was, I'll just let him tell the story.
Jason, we don't have video right now, but we're ready.
Okay, man, you have a go.
Here we go. Disposal bed, please.
So one of the things that happened when he did this is right when he went to go do it, he lost communication to the ground. And so he couldn't talk to the ground. They're like that nobody knew what was going on. Now the other guys in the orbiter are looking out the back windows, watching him do it. But you could see it. He pulled on it a little bit, but it yanked off. And it did kind of move around. So there was a slight possibility he might poke a hole in his suit. So the next one is, one of the things that happens at the Space Center is that when the mission is over with, a lot of the astronauts will come back to the Space Center. They go to your offices, and they'll pull up 20 people or so and just have a conversation. You can ask them questions just to kind of thank you for having a safe ride for them and taking care of everything. And so this lady, Chaffee, came to our group, and of course, she is like a rock star. She's been on like 4 missions, lots of time in space, lots of EVAs. And the question was, what was one of the more spectacular things you did on orbit? So I'll just see if we can just go ahead and watch it. The sun would heat them and they would kind of twitch just a little bit, and that really was bad for the telescope. So they came in with some much different ones. They had to get rid of these, and they didn't want to take them back down. So Chaffee was on this end of it, on the arm, holding it right there, and they disassembled it. And then, now what are you going to do? I got this big old solar panel. What do you want me to do? I said, just keep holding it. And they took her arm all the way out as far as they could get from the shuttle. And they said, just push. And she's like, just push. That's all I got to do. But when she pushed it, because of the length, the center went faster a little than the outer, and it flapped and flew away like a big bird. And all she could see was, I'm behind the speaker. It's not my fault. All she could see was the Earth with this big bird flying off. She said it was very cool. Now, instantly, the orbiter actually does a maneuver to pull away from it so that it doesn't hit them 90 minutes later when they come back around. So I gotta always worry about that. But that was one of her stories. All right, I'm gonna apologize now because I'm gonna try and do a few technical things, and I'll try and get through them without killing you or driving you crazy. So just say uncle, and I'll just click the button. We'll go to the next one if we get too much. But I need to give you a couple of tools so you can understand how far things apart. I'm gonna make it a stab at something that's totally impossible, but we're gonna try it anyway because we're on a cruise ship, and I just ate lunch, so I'm in good shape. So the first one I talked about we're going to talk about is AU, astronomical unit, and then we're going to go into light year. So astronomical unit is just a number they came up with between the Earth and the Sun, astronomical unit, and then every is measured. It's like its own ruler. So the question would be, how far is Pluto? Knowing the fact that on this, if the Sun was at one end of the boat and the Earth was at the other end, Mars and Venus would be on the boat somewhere. And Jupiter is just a little off the end. So how far away is Pluto? For a sticker. I take bad guesses too. You can actually kind of look at the thing there and say it's not 3 or 4. Just take a stab. Closer than 400. 20. Double that. 40. So 40 it would be 40 lengths of the boat back behind us, just to kind of give you, and everything else would be sprinkled in there. So it's a long way. All right, you're not going to guess this one. How far to the nearest star?
4 light years.
How many?
4 light years.
4 light years. How many astronomical units to the next one? 4,000? That's pretty close. It's the closest guess I had. So 270,000 astronomical units. That's kind of far. But don't worry, I'm going to take you there in a spaceship in a little bit, so don't worry about too much of that. You don't have to, we'll go there anyway. So now we're going to talk about the other one, which is a light year. Okay, this one's not too bad. It's how far, a little help from Buzz Lightyear here. So it's how far light travels, if we call it a particle. Where's my physicist again? Wave, particle, which one is it? Who's my physicist? Okay, they can't figure that out. Anyway, we'll go with a particle for right now. And so if it was a particle and it was like a car traveling, it's going 186,000 miles a second. Pretty quick. So what does that end up being? How far light travels in 1 year? About 6 trillion miles, so a little bit far. So that's quite a long ways. So here's kind of an example. Did I leave something out of that one? Nope, I got it all in there. So here's an example of how far things are away. The moon is 1.3 light year seconds. So if the moon went out, that means the sun's out. So yeah, if the sun went out, we would know it about 8.3 minutes. So that's how long the light takes to get here. So it's 8.3 light year minutes away. And now you start getting out a little further out there. Alpha Centauri at 4.2 light years. Somebody over here said that pretty much, I think. And Andromeda, and this is where Hubble came in and expanded the universe. Andromeda is 4.5 million light years away. Very, very far. All right, so here's, I said I was going to take you out there. So if I just took stuff that's available and I ignored just about everything in math and science right over here, dust particles running into radiation, Fermi's paradox, you tell me what it is and I'll tell you, other stuff equals it. If you just ignored all that and you started out, you needed a spaceship, so we'll go build us a spaceship. We'll use some space station parts, some Apollo, just what we've got. Just think that this will work, which it won't, okay? But that's not the point of this drill. The point of this drill is to figure out how long it would take to get there. The fastest thing we got going is Solar Parker Probe at 5,000, almost 500,000 miles per hour. So we're going to Alpha Centauri. We know it's 4.2 light years away. Lots of math, and we come up with how long does it take us to get there? For a sticker. You're a good guesser, but put another 0 or 2 on yours. Any answer, I'll take any answer. 100 years? Where's it? Here you go. Good guess. Very close. Almost 7,000 years to get there. He was close. He was closer than me. So that is a terrible estimate. and it ignores a whole lot. But what I'm trying to tell you is this stuff is really far away and really difficult to get to. I run into something during that 7,000 years at 500 miles an hour, the size of a pea. It's going to just go right through you like butter. And so now space is empty, but it isn't that empty. So, oh, and by the way, when we get there, it would be nice if there was actually a planet that was habitable that we could get on, and we don't really know that yet. We know something of the size of things that are around there. So this is going to really get in trouble here. I probably should take a break right here. Everybody take a breather. The size of the universe. So I've seen this number anywhere from 46 to 150 billion light years across. I had to pick something, so we'll just take 96. So the first thing to realize is the universe is actually expanding according to Hubble's law. Very good, very good. And it's getting bigger and bigger and bigger. So in reality, you can't actually get there even if you could go that fast, because it's getting bigger as you're traveling. So Star Trek's got a few problems with that. So the next question you have is, it's expanding. Is it just going to keep doing that? Is it going to go out and stop? Is it going to fall back in? It's when it falls back in and crunches, are we going to have another Big Bang? I don't know all the answers to these. That's why we have people that do astronomy for a living and not engineering. All right, so I'm going to do the impossible. I'm going to try and give you some sense of how far that is. I failed. That's the punchline, but we'll try. So this is a grain of sand. So if that were replacement of a mile, something reasonable, something we can count, how many grains of sand are we talking about? So has anybody been to the beach lately? So have you tried to count the sand out there? Some engineer did. And he came up with basically 7.5 quadrillion grains of sand on all the beaches of all the worlds. So that's a lot of sand. It's further than that, just a hint. For the guys that's guessing, low numbers. So how much sand would it take? How many Earths full of sand do you think it would take to get across the universe? Okay, we'll just go ahead and quit that. 120,000 Earths full of sand. I mean, it's amazing to me when I go to the beach and you think about how much sand is on just the beach you're at. And it's all the sand on all the beaches of 120,000. It's incomprehensible is what it is. So they do kind of look like grains of sand when you look up at them. So let's go look. See what my next slide is. Nobody look right now because I'm going to look at the next slide. Okay, it's the right one. So if you were to take that grain of sand that we had earlier and hold it out arm's length and look at that grain of sand, it would block this red circle in the sky. So what you would behind that sand would be this circle. And in that circle are tens of thousands of galaxies. Galaxies, each one with 100 to a trillion stars in each one of those. Ours has about 200 billion stars, and Andromeda has close to a trillion stars. So every single one of these is a galaxy that we see, and we are looking 15 billion years into the past. So it doesn't look like that anymore. They're not there anymore. They don't exist. The sky is completely gone, but all we have is what happened and what we can see long ago. So that's why it's a time travel machine. If you followed that, I'm doing pretty good. So here's our breather. This is what our galaxy looks like. It's another one, M51, about 31 million light years away. But this is kind of what we're in right here, the Milky Way. And this is to give you a breather from everything I just crammed down your throat. All right, so now we're going to talk about the next one. Everybody in grade school, the model of the solar system. Everybody, a lot of people built one. Cool. This is what we remember. Okay, it's not to scale, but that's okay. This is what we all think of when we see it. All right, that's all you really needed in elementary school and college, but when you start launching satellites into space, you need a little bit more. You actually have to know where they're going. And so let's see if we've got an example here. So this is what, that's going to quit someday. So this is what the sun looks like, and with Jupiter and Saturn, just those two planets pulling on the sun. Now this is the center of all this mass, and everybody thinks from that picture that the sun is right over the center. It's not. So you can see how the Jupiter and Saturn, all the planets pull on the sun and make it wobble. Well, the same thing has happened to the Earth and the Moon. Oh, the Moon orbits the Earth. That's what we know, right? That's not true. They both orbit each other. And we know this because there's tides. So the Moon is pulling all that water around and pulling. So when the Earth goes around the Moon, it wobbles around the Moon. So then you take all that and put it together, and our entire solar system is going around our galaxy. So we'll show some of that. So this is what our solar system actually looks like with all the planets and sun going around the galaxy. And this is what it looks like going around the galaxy, because everything's pulling on that. So nothing goes in a straight line, nothing. And when you start trying to calculate flying in our solar system, like solar Parker probe that's getting speed every time it goes by the sun, everything's moving. And so you have to take that into account. And there's some very spooky, smart people that do that. Light goes in a straight line, but I'm going to show you in a minute that it doesn't act like it goes in a straight line. I'm going to have an example here coming up real quick. Like now. That was a very good lead-in. Give him a sticker. So there were some Chinese astronomers back about 7,000 years ago that made an observation. They made an observation of a supernova blowing up 6,500 years ago. So they're on Earth. This thing was about, coincidentally, 6,500 light years away. And here's the star they're looking at. Looks like a star. It explodes. But that star's not actually there now, 6,500. It's moved way over here. So we see it, well, they saw it here. If we were to look at it today, it's over here. But wait a minute, it's been giving off light that whole time. So the light is actually, it appears to be bent, but it isn't. If you think of it as a particle, every particle was released along the way, and we're just seeing them as they get to our planet, and they're slowly moving across the sky with it. So they saw a superstar blow up, and this is what we see today. So if we look from Earth today, we'll see this. And oddly enough, this is about 6,500 light years across. So this is what they saw. Sorry, that's my best chop at making a supernova. And this is what it looks like today. So they didn't see this. We see this 6,500 light years later, 6,500 years from now. So I think that's pretty cool. We're going to talk a little bit about this picture here and how they got that. Okay, take a break. Math. So that's my dog, by the way. I don't know whose rabbit it is. All right, so now in order to talk about Hubble just a little more, have I gotten too complicated? Because I can tone it down if I have to. So, I mean, it's my last show. What can I do? All right, so this is what Hubble sees when it looks up at the sky. It sees black and white. So how do we get color out of it? Good question. So what we do, this telescope is meant to look at ultraviolet, near infrared, and visible. So the telescope electronically can't tell color, but it can tell frequency. And so if they put filters in each of these areas, and they know that, hey, if I get light at this frequency, it's blue. And so when it gets to the ground, they assign it blue. This is how your TV works too. So, and all cameras. Now, if you look through a telescope, you're seeing real light coming from it. So if you expose something over a long period of time, but you won't get some of these images because they stack up. So if you were a snake, I can't see infrared, but a snake can. Now, he's not really seeing it with his eyes, he's seeing it with other things, but he perceives the heat of the animal in front of him, and he sees something like this, whereas we see this. A bee sees an ultraviolet. It can see things like that. So we can't see those. Question?
So when they knew they'd see it black and white, did the scientists already know that they could use infrared wavelengths and make that application?
Yes.
See color?
Yes.
Or did they have to discover that?
No, I'm going to show you here in a second the entire spectrum, and we've known that for a long time, and we routinely look at different parts of that spectrum to learn things that we can't see with our eyes. So I'll talk about that in the next slide. So we have the near infrared, visible, and ultraviolet, and we run that through some filters, and there's some other things we get out of it, because certain planets have markers for hydrogen, oxygen, nitrogen, and we can see those in the spectrum. It has a magnetic spectrum for the star, and we can tell what kind of gases are in that planet by looking at the spectrum. And we can also see if they're moved to the side. There's a Doppler shift in the video, like a train going by, and you hear, ooh, the pitch change. That wasn't very good, was it? Somebody come up with a better train sound. Just like a train goes by, the light does the same thing. So we put sensors in each of these areas, and then we stack them on top of each other, all 5 of them, and this is the kind of picture you get. Now, realizing that 2 of those, the ultraviolet and the infrared, we can't see anyway. So we assign them a color, and we stack them in there, and we get this, which gives us a whole lot of information that's going to be more evident in some of the pictures we're going to see in a minute. So as the question was a minute ago, we have a whole spectrum of stuff out here. What does an X-ray look like? Well, we can't see an X-ray, so that actually penetrates through our body, and they can see what's inside our body by translating what the machine sees and the picture they take to what we can see, and then they can tell, oh yeah, you broke your bone today, which I haven't done. And they put up a constellation of satellites that sees all of these different wavelengths, and some still in the ground, and they stack those on top of each other to get information. We even listen with our ears through a big telescope like they've got at parks, which we can listen at audio frequencies as well that are coming that we can't hear, but they're coming from the universe. Which leads us to this. So they have something called a pulsar out there. And so all of a sudden we're listening through a radio telescope and we hear noise. Boom, 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 boom. So not many people have heard this, but this is a pulsar. This came from Parks in Australia. We added the music. But these are high energy pulses that are coming out of a pulsar that's spewing out material, and as it swings by the Earth, we hear it. And so that's what you're hearing, is that pulsar. And they can use this to determine things distance as well. Okay, we made it so far with that. All right, so we're going to smooth out a little bit, not so technical anymore. I think, have we made any astronomers in here? Probably not. So this is a galaxy, kind of like these are 2 fighting galaxies, that's what it is. You've got one over here, you've got one over here, and they're just going at it. And this is stuff you can see if you go outside. It's about 65 million light years away, and they're just ripping each other apart. So this is Andromeda. This is our local system. This is the Milky Way. The large and small Magellanic Cloud are in here somewhere. But they're getting ready to scrap. So did you want to see that? Okay. Is going to smash into us, and it's way bigger, as I mentioned earlier. So that's going to happen, and I think we should all prepare for that because it's in about 4.5 billion years. By the way, it isn't going to help what you're in, by the way. It's going to happen. All right, so we'll take a breather there, and we'll go ahead and look at some pictures that are coming out of Hubble because you can't study it for too long and not look at some pictures. So this is a spiral galaxy that's a little more armed than ours, so it's like ours, but it's got some bigger arms. It's about 76 million light years away. Then we got some nebulas. These are things that have blown up. So there was a star right in here that's blown up, and we happen to see it flying apart. A couple more nebulas that are close to each other, about 4,000 light years away. Not sure what this is, but lost in space.
Now, a new Hubble image shows the region in unprecedented detail. Capturing the multicolored glow of gas clouds, wispy tendrils of dark cosmic dust, and the rust-colored elephant's trunks of the nebula's famous pillars. With these new images comes better contrast and a clearer view for astronomers to study how the structure of the pillars is changing over time. Hubble also has an additional New Year treat for us. The telescope gazed at the same area in infrared light, allowing it to pierce through the obscuring dust and gas and unveil a more unfamiliar but just as amazing view of the pillars.
So this is the Pillars of Creation. It's pretty famous. Has anybody ever seen that before? So yeah, but the infrared is actually coming through the haze and stuff that around it, and they get pictures of it. But without the infrared, we would never know that. So, all right, so we're going to go look at a few more. We have two kind of galaxies close to us. I think they're defined as dwarf galaxies. The larger Magellanic, I'm going to say that because that's who it's named after, Magellan cloud, and the smaller one, and then Andromeda. I'm going to find him with this before we get off this boat, maybe. And here's one with just bigger spiral arms. Now they're just looking out in the out in the universe, and they find them and they zoom in on them, and they get these pictures. So these are some of the older type pictures we were getting, and these are some of the newer ones they're getting. Big difference. All right, I'm going to go ahead and hit, what are we doing on time here? I got a couple of minutes. Maybe I'll jump ahead and do Pluto just for the heck of it. So this is bonus time. Now I would do one on James Webb, but then I really didn't want to go back and do Hubble after I did one on James Webb. And James Webb, I'll tell you one interesting thing about James Webb. For most payloads, if you have something, a single point failure is if this fails, end of mission. You know, like the shuttle, there's two big SRBs. If one of those fail, it's end of mission. So it's called a single point failure. Nothing you can do about it. Most missions are considered very risky if they have 40 single point failures. All 40 of these have to work. Now some of them are like batteries, so it's pretty low risk that they're going to happen. James Webb had 256 things had to go right, and all of them went right. And they are getting amazing video out of that thing. And the detail with which they could do it, being the mirror, is 3 times the size of Hubble. They're getting huge amounts of detail. So we've not even begun to see some of the stuff coming out of James Webb. This is James Webb in the factory. You can see how big the mirror is compared to the other guys that were looking at the other one earlier. And these are some of the pictures that are coming out of it. James Webb's only been up a couple of years, I think. I don't know the exact launch date. You caught me off guard there because I should have had it. But I would like to do a whole presentation on James Webb, and so that's why I kind of left some of that out. And like I said, if I started with James Webb, you wouldn't really want to go back and look at some of these others. Even though Hubble is still a very powerful telescope today compared to everything else. So I'm going to go ahead and jump forward, then I'll come back since I got a little bit of second here. Quick. So I wanted to talk about Pluto New Horizons since I actually helped launch it. It's flying toward, it was Pluto New Horizon, anybody? It's on your badge for your satellite club. Did anybody get a badge? Who got a badge for satellite watching? And we have a club, a whole club. Well, people that got badges. So this is Pluto New Horizon. We launched it almost 10 years, well, about 11 years now, because it's already gone by. And it was going about 30,000 miles per hour, and it could not stop. It was designed to fly by Pluto and without stopping, because it takes gas, and they would have never got there if they would have put that much gas on there. So to get there in a reasonable amount of time, that's how they had to do it. So it literally took pictures as it flew by and filled up all their memory, and then after it got by, it turned this big dish around back to the Earth and started beaming them back. And so we're still getting pictures because it took so many pictures when it went by. 2 weeks, I'm pretty sure 2 weeks before they got there, the computer failed. 10 years, 2 weeks before they get there. So all the guys were scrambling around. They have a backup computer, but they're scrambling around and found the problem with the software, rewrote the software, sent it up, and then all of them took a break. I'm sure they took a big break after that. That would be horrifying. It's been flying. You've been sitting there watching it for 9.5 years, and all of a sudden, poof. But we got some good. Now this is the thing about going a straight line. They don't go in a straight line. That's not how you get there. And here's some of the images we got back here. This guy keeps showing up. And this is of its moon. Now it turns out there are other things out there of this size, and so that's why Pluto got degraded into not being a planet and called a planetoid, because really there are other things out there of equal size that have small moons and running around, and so it's a whole class of stuff flying around out there. This is a surface picture. Nice place for a house right there. Ooh, little Debbie on a cruise. I was supposed to see that. All right, so I have some time for some questions. Did I cover everything? Oh, some final thoughts. So, what is all this stuff out there? What's the reason for all this? Does anybody know the reason of why all this is there? It's just interesting to me. And, what's here? If this is everything we know of, can see, feel, touch, what's there? If that's, what's there? Is there a wall here or something? I don't know. Everything's moving out. Where's it going? Where's it coming from? An astronomer was here, he would tell you the answer to those, but I just as an engineer have these questions. And then you consider, however you want to look at it, 15 billion years, 97 billion years, we are just so far, we're just a wink, on the cosmic time. So just some stuff for you to go home and keep you awake at night thinking, because I know that's what's going to happen. All right, so we have some time for some questions. Oh, I want to do one other thing, and I think I'm going to do it before the questions, so I make sure I don't run out of time, which we're doing right on time. Who has not got a picture? I give away pictures, and they come in the front row, they ask questions. Who has not got a picture? All right, okay, I'm going to have to narrow it down just a little bit. Birthday in August. Are you August? Okay. Have you not got a picture? Now you have one. Any other August birthdays? We got one back here. Well, I'm going to give them away till I run out. I should make you have a birthday who has March, and you can remember my birthday to send me a present. Okay, I got about 4 or 5 more. I'm going to go to the back and work my way forward, because all the time I've been working my way from forward to back, so it's fair that I go to the back and work my way forward. If you don't get one, please yell at me or something. I'll find some way to... August? Okay. Well, let me finish this, and then I'll get right back to you. One August here. I don't really know why I pressed August. All right, I'm going to get over here, and then I'm going to come in here, because I've given a lot of pictures in here, so everybody knows that's true. One more back there. Can you pass that one back? Or one of them back? I got 3 more. Next time I'm just going to print some more pictures. All right, I'm coming over here. This is going to work out, isn't it? Pretty close. I only have a couple of people that are unhappy. All right, one more. Tell me there's no more. Anyway, act like there's no more. Did I do okay? Yeah, I didn't have any real way to pass that out, and I wanted to find a way to be fair about it, and I don't know if that's fair or not, but it was the only way I came up with. All right, so we'll go ask some questions, and I have these little nice big stickers here for people. Ooh. I should just make those picture stickers, and it'd be like large stickers. Go ahead. So the question is, the images that we're receiving from Hubble and these telescopes, have we got things that have really shocked the scientists to find this out? There is so much information that they started packaging the information and making it available to universities so that they could start looking at it. But they have found all kinds of stuff. I can't tell you them because, remember, I said at the beginning, I'm not an astronomer. So So I'm an engineer and I have studied astronomy in school, but I'm not going to qualify. But they have learned so much, and I think at a minimum right here, I think I enjoyed the slides, the pictures. I hadn't seen some of those until I'd done some of this research, just how amazing it is out there. My theory about life on other planets. You know, if you ask questions long enough, you get in trouble. So, the question is, what's my theory? You know, okay, I'll just tell you what I think, then you can just do. I just showed how long it takes to get to the nearest star. We started transmitting signals into the universe on radio during World War II, during World War II. Everything that's transmitted is basically on its way outside of our solar system, has been traveling for 50, 75, 100 years. If you were to jump all the way out there real quick, you could receive those signals and you could see what happened on Earth, 75 to 100 years ago. We don't have anything like that coming back at us. Now, there's a couple of reasons for that. Well, it's a long way. We have modern technology for the last, let's just say 200 years for the heck. That's all we've been able to send anything out. Maybe they're the same boat. Maybe they just don't care about us. Maybe they're not there. Maybe they're a different life form and they just don't care at all. I don't know the answer to that. I wish I did. I would love, as an engineer and a scientist, to find something like that. There's always all the movies that talk about who wins when two technologies get together. So I don't want to have the answer to that. But as an engineer and as a Christian, I would like that, but I have different views on that, and I'll keep those to myself. So next question. Was that a good enough answer? Okay, we'll go with that. I'm going to slide through here.
You mentioned that these planets are so far away.
I didn't say they can't possibly get to them. I said it's difficult.
You said, are they working on a system? Also mentioned Star Trek and hyperspace. Not very good to get to the planets. Is there any system where to increase the speed of the
So the question is there a better technology to go through space than basically a action-reaction, something like warp speed or something in some of the movies? We don't have anything like that yet. There's some different types of drives that they're coming up with that might be more efficient. If you go back and look at F equals ma, to accelerate 1 pound up, the force required would basically be all the energy on the planet. So it's a lot of effort. We don't have that, but the first question was, did I say that it's impossible to get there? I proved you could get there. It just takes 6,000 years. But it would be very difficult, and it would be very hard to do. It might be the right thing to do. It's difficult to get to the moon. It's difficult to get to Mars right now. So we're going to have to come up with some new technologies, which we do all the time. And hopefully that will provide something, I hope someday, that will change our view on how to get there. At one time, people said if you go 60 miles an hour in a car, you won't be able to breathe, and that we didn't need more than one computer in the entire country. I think that's wrong, since I have two. Let's open wallet. Next, I got two more, and then we're going to go from there.
This is a question, and I suppose I'm looking at it from your engineering background. This is a very expensive program. So going forward, what is going to keep the funding going there? Is it our desire for knowledge? Is it our desire for possibly minerals? Is it adventure tourism? What's going to keep the money focused in that direction?
So the question is, obviously this stuff is very expensive to do and very risky. So what motivates us to keep doing that? What keeps the money flowing to do something like that? Well, in a capitalistic system, it's based simply on the fact that they think they can make money. If I put up a satellite that broadcasts cell phones, I make money. There's a model for making money. It doesn't always make money because some of them fail. TV, communication, some things have to be on orbit to do that. The video, but it's expensive. The biggest one we've done is the Apollo program, driven totally by politics. So there has to be some motivation. Right now, SpaceX and Amazon are basically looking at it from a money-making proposition. We're going to make money off this, and they will. Is there enough money out there to go to Mars? Well, Elon thinks that there is. That's what he wants to do. Jeff Bezos is putting money into it left and right. It is a difficult business to get into, very risky, as you can see from some of the failures they have, and it's very public when it happens. So we'll see if the money keeps going, and when it doesn't, it stops and it doesn't go any further. But TVs used to be like, flat screens used to be like $4,000 or $5,000. You can go get one at Walmart today for $500-600. So technology has brought the price down of stuff, and that is starting to happen with the space industry. So one more, and we're going to close it up so I don't get in trouble by the next group.
Is there any awareness that the U.S. Russia has made any energy research in this area? Do we know?
Okay, the question is, what is Russia's goals or participation in the space industry? I don't know, that's a really political question. I'm going to go as far as this. At one time, Russia, a few years back, was saying, we're not going to take you to space station anymore. They still do. They make money off of it. So no matter what people say in public, and when they get back down to it, the dollar kind of rules. And so, yes, we are flying stuff to the space station on Russian vehicles that are still there to now. When they said we weren't going to have a partnership between them, fly your own broomstick was Elon painted a broomstick on the side of his rocket to pay people. From an engineering perspective, engineers speak the same language, even if they speak Russian and we speak English, math, all that stuff. We get locked into a problem. If they can help me solve my problem and I can help them solve theirs, we like to fix things. And so the scientific community from a research has continued to cooperate for space station. And when it meets both people's goals, they will cooperate and get together. When it doesn't, they won't. And I hate the fact that politics get in there and stop a lot of that for no reason whatsoever. And I'm not going to talk about that anymore. So I've enjoyed this a lot. I hope you have. I'm going to try and go on another Azamara cruise. I've got one in November, so I'm going to plug that one. You come in November out of Spain and come to Miami, and you come by my house, and we'll go see a rocket launch. Don't do that. But anyway, I had fun. I hope you did too. Thank you very much.